without further delay, we should start. So this morning you'll have a lecture by me. My name is Benoit Roux, and Aaron Dinner, and actually we are missing a name.
He has his own. Shaney.
But can you say his full name?
Olaseni Sode.
That's right. He's going to also contribute to this lecture. By mistake, this is missing there. So we're going to try to do an overview of these, the classic and the more recent development of methodologies for treating molecular events and molecular processes that are intrinsically rare. The most naive reason why things are rare is because they have to sort of cross a large energy barrier to go from one state to another. So that's one reason why things can be rare. But from more like a statistical mechanical point of view, sometimes this bottleneck could be entropic and not necessarily energetic. And so at some point, you know, the theory will show that this is not really just about energetics. So a good example to actually illustrate these methodology was ion transport in this small system called the Gramisalide channel. So it's a molecule that can span lipid bilayers, and it has a hole in the middle, so there's a pore, and ions can actually diffuse along the axis of the pore, and they diffuse fast enough that actually you can measure the current through one channel, meaning that you will have about 1 to 10 million ions per second crossing the channel under some biophysically meaningful conditions. And so the current is related to the rate at which ions can cross this channel. And if you look at the molecular detail, you'll see that there's lots of steps in there for an ion to actually cross the channel. There's different stages of coordination. And so you'd like to understand that from a physical point of view. So the classical phenomenology for an ion crossing this kind of channel is that the ion will hop around between different energy barriers. And that thing that is here, this line, this wavy line, is often in the traditional literature is called the free energy profile of the ion along the axis of the pore. And the rate to hop from one stable well to another has often been pictured as being described from the point of view of iron rate theory. On the other hand, it's pretty clear that the ion is undergoing a kind of a diffusive motion along that coordinate, and so it's not really just appropriate to talk about iron rate theory. Perhaps it's more appropriate to talk of a continuum electron diffusion theory or Nernst-Planck diffusion, where the ion would rattle behind, you know, from one well to the other, maybe even rattle at the top of the barriers. So the physical picture can vary in different ways. And for example, if you consider the crossing of only one barrier, you could say from iron rate theory or transition state theory, it depends on the frequency in the well, the activation energy, and essentially it's an Arrhenius Boltzmann factor for the rate. If, on the other hand, you describe the motion more like a diffusive motion, where you rattle at the top of the barrier, you might want to use something that's more like a Shmuelkowski equation, or to get a Kramer's rate, for example. Note that, in fact, the free energy barrier in both cases is just a copy and paste, cut and paste, and so in both theories, this underlying free energy profile is actually a very central quantity, and we'll see why very much in a minute. So let's step back a little bit now from the channel, and then just look at the simple two-state problem. Imagine you just have a two-state problem. So you have a state A and a state B. This is a closed system, so it's jiggling around. It's submitted, let's say, to some sort of dissipative and forces, perhaps from some sort of heat bath or something like that. So this is not an isolated system. And the system can go from state A to state B, given the phenomenology would be that there's a rate K1 to go forward, and then there's a rate K2 to go backward. And if I simulate this process, you could imagine that, you know, you spend time in the state A and then you jump to the state B and so on and so forth. If I make a histogram of the X as a function of time, you know, so I will get two peaks. Essentially, there could be two probabilities or two states. And that's the average histogram. Now, if you want to describe this rate process from a more statistical mechanical point of view, what you would want to deal with is, for example, population operators. So that is H sub A would be the population operator to be in state A. H sub B would be the population operator to be in state B. And so from the phenomenology, it's clear that the population are just these ratios, these simple formulas from rate theory. That's simple. But now how do we compute these rates from a statistical mechanical point of view? And what you would be tempted to do is to write the flux as some sort of density times the velocity. That would be the forward flux. But the problem with this formula is that it just looks at the flux at the top of the barrier, but it doesn't really account for the fate of the trajectory. A more complete formula for the forward flux would be, yes, I am at some position, I have a velocity, but also I worry about the fate of the trajectory at the time tau later. Namely, I will put the population operator there. So if I did not make it within the basin B, somehow this flux doesn't count. So this is really the flux from A to B. So if you take this formula and you start to expand it, so this is a trick that happens a lot actually in statistical mechanics as applied to these simulations, is that you'll have a complicated bracket like that. It's a complicated formula. If you know it's here, it's up here. And what you do then is you introduce a numerator and a denominator, ratios that cancel each other. So you look, this is what we want. I introduce this guy here, but I also introduce it at the top here. So basically these two guys cancel. And then below this guy I introduce this thing, but I introduce it also here. So these two guys cancel. But that looks like a trivial manipulation. We're basically multiplying by 1. But the nice thing is that when you have the ratio of two things like that, it becomes a conditional average. For example, here I have a quantity times delta function times z dot. Then here I have the average of the delta function times the z dot. And so it becomes, if you take the common part of that, it becomes the conditional constraint for performing the average. The same way here, you have the delta function times these guys, and here you have the delta function. So essentially, it's the average of these guys conditional that the delta function is satisfied. And so these ratios are very powerful because they really break down the computation very, very much. And so the way this happens is that you would say these two guys become transition state theory, and then the leftover, which is a little bit more complicated because the time tau appears, now it becomes what people call the transmission coefficient. And if you assume the transmission coefficient is 1, which means that when I'm at the top of the barrier and I move forward with the velocity, I don't worry about the fate. I just count this as a 1. Essentially this guy disappears and you're left just with transition state theory. And so, and in the transition state theory, you can see there are really two factors. One is more structural. There's no z dot here, so there's no velocity, no momentum. And this one has the velocities. So the part that has no velocities, no momentum, is only a structural average. And as you can see here, the W function is the potential of mean force, or the free energy profile that shows up here. And so this is the overall structure of the theory. I just gave you an overview from a kind of an intuitive or naive point of view, but in fact, that kind of formula was derived in the 70s by David Chandler, and it's actually explained very clearly in his book. If you actually worry about the fluctuation of the concentration of A and B, and so you write you use still the population operator, but now you look at the deviation of the population away from equilibrium, and you write things like that, what you're going to see is that there's an overall relaxation time, and the formula for the rate comes out naturally by looking at these considerations based on these fluctuations. And so this is the more rigorous pathway to derive these kind of formulas. So I showed you before that one of the central quantity is this potential of mean force, which I typically call W. We call it W because it's actually a work function, so that's why I often use W. And this is actually, in part, the reversible work theorem, is to say that the potential of mean force, which is related to the work done by the mean force, so from some point of view, it has a mechanical aspect to it because it's the average work you do from the mean force, is related to actually the density histograms, these probabilities. And so on the right side, that's more like the statistical aspect of things. And that's a reversible work theorem. Is really not a an innocuous or you know, anodyne kind of statement to say the work done by the mean force is related actually to this probability histogram. It's a very, very powerful relationship. And so what you can do is imagine as you know from the calculation of the rate, we need this potential of mean force. We need to calculate the potential of mean force. How are we going to calculate that? Well, what we do, one way to calculate it is to say, okay, this is true when I have the real system with no bias, but I'm free also to introduce some biases. I could, for example, introduce a kind of a parabolic or quadratic potential that biases the system around a little zi of my choice. If now I introduce this little potential into the system, the overall potential of mean force will be still the correct potential of mean force together with the biasing I've introduced. And on the right side, what we will have will be biased histograms. They're not the natural histograms anymore, but the fundamental relationship still holds. And so what you will see is that you'll get these biased histograms, these rho sub I, and the way they will be biased is very simple, is that they are the correct histogram multiplied by the Boltzmann factor of the biasing potential that you introduced. And so it's actually kind of easy to imagine now what you need to do is so you can invert this formula using the potential mean force theorem, and then write that the piece of potential mean force is minus kT the log of the bias histogram minus the potential that used to bias it. But there's also an unknown shifting constant because you don't know from one window to the next how much this overall potential mean force is changing. This relationship is true overall with an offset constant. So how do we actually apply that in practice? So imagine we have our system before. This is the histogram that I was talking about before. And so you imagine you run still the system, but you force it to jiggle around minus 2.5. So it gives you this pink histogram. I also force it to now to jiggle around minus 1. And it will give me this green histogram. I could force it to jiggle around 0.5. It will give me this blue histogram. You see there. And I can force it to jiggle around 2. It will give me this magenta histogram. If I do minus kT the log of all these histograms and I remove the biasing potential, what I get are these pieces. You can see clearly they have shapes that are very common, but the offset constant is unknown. So for example, the blue histogram gives me a part of a whale, part of the barrier, but when I get to the wings of the histogram, things become noisy and unreliable because there are only very few configurations that were used to do that. On the other hand, then, the green histogram can pick up where the blue starts to be uncertain and will give me this piece of potential mean force. So essentially by piecing these guys together, I am able to create the potential mean force. The only thing I have left to do is make sure that they actually overlap. And so what I do is I'm going to shift them vertically until they overlap. And so then you get the piece from the magenta one that is good like that, all the way to here. You have the piece of the blue one, which is good all the way to here. The green one is from here all the way to here. And then you get the red one that's the rest. And so at the end of the day, what you're going to do is actually lump this thing together in some sort of a mathematical way that's called, for example, the weighted histogram analysis, the WHAM, which will utilize all the data to construct a single curve that is the best curve you can do with this. Or, but manually, what you could do is just throw away these little glitches, and it will give you your potential mean force. So basically, if you keep only the best part, you would get that. So this is the way to get the potential of mean force. Once you have that, let's see what happens when oops. If you want to apply this methodology in the case of the Gramasanine channel, for example, so imagine you're a sodium ion, you're in the pore, and you need now to move forward. So I calculated the potential of mean force of the sodium ion in the pore for a little piece of the part of the pathway. So this is from 0 to 1.5 angstrom. So this is only a small piece of moving along. This is one energy barrier. And you can see this is like, about 4.5 kcal per mole. So that means that the process is not super fast. I mean, you could probably simulate this on a computer by brute force and just observe the ion jumping around over that barrier, but it would take some while. On the other hand, it's possible to actually cut through weighting this and by accelerating the process to compute the rate. So now that we have the potential of mean force, what we have to do is go to the top of the barrier Right? So this part we can compute directly from everything I've given you. This is just the movement of the ion along the axis, so we can do this all on pencil and paper, because this is in Maxwell-Boltzmann, when you have a canonical ensemble, the velocities and the position are decoupled. So you can compute this directly for any system. And so you can compute the transition rate, the transition state rate for that system. Now, what about the transmission coefficient? If you go to the top of the barrier and you want to compute what is the likelihood that the reactive trajectory will really become reactive. So it's possible to rewrite the formula that we had before like this. Essentially, it becomes a population operator. It's a Heaviside function at the time t relative to the barrier position, and then you have to subtract at the time minus t, like that. And so if you do this, and the average here with the plus sign means that I'm averaging this conditional to having a z dot that is positive. So you see z dot times the Heaviside function. So I am at the top of the barrier, I give a positive velocity, and then I let it go. And then the system can try to go forward, it may jiggle and rattle, it may go backward. And so this is the kind of thing you have to compute. So when you start this, the distribution has these kind of velocities. You see they're positive velocities. It's not just a pure Maxwell-Boltzmann velocity, it's actually a biased forward velocity. It's biased forward. Once you do that, this is essentially your transmission coefficient. So essentially at time 0, it starts very close to 1, because as soon as you're at the top of the barrier, you push it with a positive velocity. It may look like for a small instant that the trajectory is going to be reactive, because you do end up on the product side. I mean, like you just push it. So obviously you will be on the product side. So it will be close to 1. But then it will drop fast. Why does it drop fast? Because there's going to be a kind of a caging effect. As soon as you push it, things will react and it will jiggle back. And so this will drop very fast. And then you sort of rattle at the top of the barrier. Some of them will go to the product. Some of them will go to the reactant. And so this thing settles down. In this particular case, it settled down around 0.11, which means only about 10% of the trajectory that transition state theory would really think are reactive are really reactive. The other ones are just falsely, they're seemingly reactive, but they're not. So the real rate is transition state theory times about 10%, 0.11. So using this and the transition state theory rate, it's possible to compute the full rate of a sodium ion across that barrier, for example. Now, if you could just only compute things and then leave for home and say, okay, this is my work day is finished, I'm done, that would be kind of boring, because in fact, in theory, you can always use the computation to learn more about the system. It's not only the purpose of the computation to just reproduce numbers, but actually to understand why they are the way they are. So we compute rates because we're interested in mechanism. And so if you look at the transmission coefficient I was telling you before, it's this kind of a Heaviside function, but in fact you can reformulate it. It becomes the number of trajectories that went from the reactant to the product minus the number of trajectories that went from the product to the reactant divided by the total number of trajectories that I ran. So this is from the reactant to the product to the reactant. Others were from the reactant to the reactant, and others from the product to product. So here I show you an example of each. You see, I start here at time 0, and I push it forward. If you look, actually, all these plots, at time 0, the velocity, the slope of the curve is positive. That means that I was pushing it. They all have a positive velocity at time 0. Now I follow it forward in time, and you can see this one goes forward. If I follow it backward in time, it was coming from the reactant. So this goes from the reactant to the product. So this is this guy. But even though I push some of them with a positive velocity, the circumstances of the system are such that, in fact, this was a falsely reactive trajectory. It bounced back and scattered back to the reactant, and in fact, it was coming from the product. So these guys actually, they count as a negative for your transmission coefficient. And then you have others that are completely misfires, that, you know, it just went from the reactant, it nearly crossed, and actually it bounced back to the reactant. Or in fact, it was even more misleading. It was coming from the product. It looked like it was jiggling there, and in fact, it went back to the product. So only the first one is really a reactive trajectory. Now, what can we learn with this? Well, what we can learn now is this. Of course, you know, there I am talking about the sodium going along the axis of the channel. And that means the language we use to describe the reaction is based only on the position of the ion along the axis. That's a one-dimensional thing. Obviously, that system has many, many more degrees of freedom. And so, as soon as you project the dynamics onto an order parameter like that, and this is a one-dimensional one, but sometimes we want to project on 2, 3, or even, you know, many more dimensions. Typically, we project the reaction on a smaller subspace than the full number of degrees of freedom. And so, there are things that are happening among all those degrees of freedom that I was not particularly monitoring. And now is the time to actually look at what was happening. So for example, there's the ion moving along the channel, the axis, but it can be off-axis. Obviously, it's free to move off-axis. There's nothing that prevents that. So if I start to look at within the cross-section of the pore, where was the ion when it was reactive, when it was not reactive? And so here I map always, so this is the reactant, this is the product. When you move by 1.5 angstrom, actually, you go from a well that's around here to a well that's around here, because this is an helix. So the wells are not really along the axis, actually. It's moved, the ion is following an helical pathway. And so this is the reactant, this is the product. And only the pluses, the little crosses, were really reactive. Like all the circles, the triangles, were not reactive. And now it makes it clear that the pluses are actually concentrated in the center here. You see? So it's not only that I have to cross along the z-axis, but the only way to be successful was that being in the cross-section of the pore, I had to be close to the middle. If I was too much on the edge here, these were all misfires. You see, all those are misfires, only when I'm close to the middle. So that's like an underlying structural reason for the big decrease of the sort of the productivity or the reactivity of that process, that the transmission coefficient goes to 0.1. The transmission coefficient goes to 0.1 because we picked the z-axis as our order parameter. If we pick another order parameter that, it could be a better order parameter, then maybe the kappa would be only 0.5 or 0.8. But that would mean that probably along that other order parameter, there would be a different potential of mean force. And there would be a different transition state rate. The product of the transition rate times the kappa is actually invariant. That's a property of the system. So when you pick different order parameters, you change the relative value of these ingredients, but the product itself actually remains an invariant. That's a real property of the system. So if you do your job right, and you do the whole thing for a few order parameter, the overall rate should be invariant. That's seldom done because it's a lot of work to actually do that. But often it's tempting to describe the dynamics of these order parameters as a kind of a generalized Langevin equation. And it's a bit of a phenomenon. You can derive that from fundamental principle, although in large complex systems, it's more like a kind of a phenomenological framework that people sort of hang ideas onto. So it would be saying that, yes, the motion is described by a potential of mean force, and there is an overall dissipative effect, maybe with some memory in that system. Sometimes you can compute that memory. For example, here I computed the memory of the sodium ion at the top of the barrier in the Graham-Sandwich, and you can see actually it loses its memory very fast. In about 0.5 picosecond, it has forgotten the value of the forces and the velocity. So if this is a sharply decaying function, you could basically take it out of the take the velocity out of the integral and turn this into a delta function. So essentially, that becomes the Langevin equation. That's the Markov hypothesis with respect to the noise. And then if you say the noise is very large, and in fact this poor particle is getting kicked around, you could say, in fact, the mass, which is the inertial effect, the swing, the fact that you have a swing, could be negligible. And so if you throw this out, you can rewrite this basically as a Brownian dynamics. So you can see that this hierarchy of simplification, or layer by layer, brings you to a simpler model. At some point, the dynamical model is definitely simpler. Every time, even in these multi-dimension, you will end up with these kind of potential mean forces, you know, which could be in many dimensions, meaning that they actually encompass many order parameters. And the hope is always that if you increase the dimensionality, presumably these simplification about the type of dynamics will help you out. So, for example, I showed you that the position of the ions within the cross section is important for the productive rate, and so that means that in principle we would need to have the potential mean force of the ion not only along Z but actually within the space X, Y, and Z in three-dimensional space. So it's possible, for example, to compute the potential mean force of ions with respect to the entire structure of the channel. So obviously this is a more difficult calculation to do, but it's possible. And so from that point of view, you do include the rattling and the motion within the cross-section of the channel. And now Aaron will talk to you about more advanced methods actually built on these principles.
Benoit will come in. Is that tight enough? Is that okay? Okay, so I'm Aaron Dinner, and as Benoit said to you, what you can do is calculate free energies and ultimately rates using, for example, umbrella sampling, where you're forcing yourself along a particular coordinate. So in the ion channel that Benoit showed you just a moment ago, it was the line going along the channel, right? If you were doing, say, a chemical reaction, it might be like a bond length for a bond that's breaking, for example, right? The issue is that you might choose that coordinate because it makes kind of intuitive chemical sense to you. And that would be what we call an order parameter. But very often what happens when you start forcing yourself along that coordinate is something like what's going on in the black curve here, which is you would start off in the reactance, and instead of hopping over the barrier here and following this kind of minimum energy or minimum free energy path, you'd actually be driving yourself along here because you're really keen to follow the coordinate that you put in. And you don't know about all these other hidden barriers, if you will, in a complex system. And so what will happen is you'll drive yourself along there, and then if you're unlucky, you'll just get totally stuck, and if you're lucky, you might actually relax down to the product, and you'd see a lot of hysteresis, basically, here. So what I want to talk to you about is how can we avoid this kind of situation and actually harvest paths that are really going to go along the real reactive kind of directions, even when we don't know a priori what these hidden variables are, all these other coordinates. Okay, so the real big idea that emerged in the late 90s is that rather than starting off in the reactance and just marching forward in time, running a direct electrodynamic simulation, what you want to do actually is deal with the whole reaction path at once, in essence. So to be able to make operations on a whole chain of states that are leading already from the reactants to the products and maybe relax, for example, what's going on in this transition state region. Okay? And the whole challenge, of course, is figuring out how to do those kind of operations. So let me tell you kind of practically what you can do, at least for many systems, and then what we're going to do is we're going to go back and we're going to justify that procedure theoretically. We're going to make connections to the kind of reactive flux and rate ideas that Benoit talked about. So imagine that I was lucky enough to have one molecular dynamics simulation that happened to have the reaction of interest, the chemical event. that I wanted. That would be like this red kind of line here, which is representing a whole chain of states going from the reactants to the products. What I could do is I could pick up some phase space point somewhere up in the middle of that trajectory, perturb it a little bit, say by changing the velocities a teeny bit. And then, because it's on a computer, I can reintegrate from that phase space point, say forward or backward actually in time, and I can ask, did my new trajectory also contain the reactive event of interest, right? So in the bottom example here, my blue trajectory that I generated, which starts off in the same place but diverges a little bit as I go forward and backward in time, it's still containing the reactive event of interest. I know that because it ends up in the reactant and product basins. Whereas maybe I chose slightly different velocities here when I perturbed. And in this case now, instead of making a successful crossing through the transition state, now this trajectory is effectively falling back into the reactant well. So it's no longer a reactive event. And what I would do is I would just throw away this blue trajectory and try again with different random perturbations on the red trajectory. Okay, so that's the idea. Any procedure that involves some random change and evaluation is what we call a Monte Carlo procedure, right? Probably a lot of you have come across that in the equilibrium sampling context. Okay, so let me just kind of give you some sense that this can work. I don't know if it will run automatically. So this is a system that we did some time ago, actually, where it's a DNA repair protein bound to DNA, and you can see that you can simulate a pretty good-sized conformational change that would take milliseconds, basically, of waiting for this nucleotide flipping event. Okay. So the question that now I want to spend most of my time on is, how do we actually know that the trajectories that are coming out of the procedure that I just told you that they're good, basically, that they represent real dynamics trajectories that I would get if I was lucky enough to have the right combination of momenta in a direct simulation. Okay, so like I already said, what we're basically doing is a kind of Monte Carlo procedure. Traditionally, Monte Carlo procedures are sampling an equilibrium state. So you might have like a liquid, like argon, for example, and you would move, say, the argon atoms a little bit. You'd accept or reject those changes, and then the configurations that would be sampled would sample from, say, the canonical ensemble, right? If you think all the way back to general chemistry, actually, what's the definition of chemical equilibrium? It's when the forward and the backward rates are equal, right? Usually we don't actually have our hands on the macroscopic rates in a simulation, and so what we do actually is we enforce, in order to know that we'll get to equilibrium, a stricter condition, and that's what's called detailed balance, a microscopic reversibility. This says that the forward rate and the backward rate between any two microscopic states, so configurations, for example, is equal. And if we know that, then we know that our Monte Carlo simulation is going to converge to equilibrium. Like I said, it's a sufficient but not actually necessary condition. Typically what you do if you want to figure out how to satisfy detailed balance is you actually break up this transition probability. I should say, so this is the equilibrium probability, and then this is the probability that I go from this state x to some state x prime. Typically what I do is I break this up into a generating probability, that's the likelihood of making that trial move, and then an acceptance probability, that's the likelihood of taking that trial move. And so typical choices are to choose the generating probabilities to be symmetric. That says like I have an equal chance of moving this way or that way, for example. And then if you plug those in, and then have a Boltzmann probability for equilibrium probability, then a typical acceptance probability that you might choose would be the so-called metropolis criteria. The minimum of 1 or the ratio of the Boltzmann probabilities. Okay, so now what I want to do is I want to test for detailed balance not in a configuration space, but instead in a trajectory space, a whole path space. Okay, so then what I have to do is I have to learn how to calculate the probability of a path. Okay, and we're going to basically use the same kind of thinking over and over again in the next couple slides. It looks like a lot, but it's really actually just kind of bookkeeping. So once you kind of get into the thinking, then it's easy to see how it works, and you're going to have the, I think you're going to have the slides later, so you can always go through it. I'll go a little bit fast. Okay, but just, this is the most important thing. So the path probability, what's it going to be? It's going to be something that picks out that I start in the reactant basin, the A basin. Then the probability of my first point that's going to anchor me in the canonical ensemble. And then a product over transition probabilities that take me from one point to the next in the trajectory. And then a function that's just going to pick out and force that I'm in the product or B basin. So these H's, they're 1 and 0, depending on whether I'm in or not the basin. Okay? And then this is the real sort of meat of the probability. It's just the Boltzmann probability for one point, and then a set of transition probabilities from one step to the next. Okay, so then what would happen, if I just go back for a moment, if I'm doing this procedure, I'm picking out some point, which we're going to call J in the slides, and then I've got to figure out what's the probability that I generated these new path halves, this new piece and this new piece, okay? All right, so that's what I got here. This is the probability of generating by a electrodynamics integration the forward part of that trajectory going from point J that I picked out, that particular phase space point, and then going transition by transition along those steps, just multiplying them. And this is then the backward integration. I'm starting, in essence, at J, and now working my way backwards. I stuck a little bar there to indicate that I'm going backwards. And then, what we got to do is we've got to basically split all of those, flip all of those backwards probabilities so that now I can write the whole thing forward in time, so it's easier to think about. So that's what's shown here, is that basically I can use the reversibility of my integrator, the microscopic reversibility of my integrator, to flip, in essence, the backward time part of the trajectory. So I'm writing that product with forward transition probabilities. And when I do that, it turns out that I pick up a ratio of the configurations that are on the ends of that trajectory segment. Basically, I'm changing my anchor from being like the J point to being like the 0 point. Then, if I plug all of this in, once the dust settles, the final path probability that I get for the new path is going to be the probability that I generated the perturbed point, where I changed things a little bit. So that'll be the details of how I messed with the momenta right up at the top near the transition state, divided by the Boltzmann probability for that. And then I can plug in, and I can test for detailed balance, and an amazing thing actually happens when I do that, which is that all of these different factors actually end up canceling out, and the acceptance criterion, if I have a reversible dynamic, turns out to be just asking whether the new path goes from the reactant basin A to the product basin B. So, although it's kind of a lot of tedious kind of bookkeeping of probabilities when you're actually thinking about whether the procedure works, in practice, at the end of the day, all you have to do is actually test, assuming that you've got a legitimate scheme for perturbing the velocities up by the transition state, whether you actually got a new trajectory that spans the basin. And something I should say is that the reason that this is computationally advantageous is that now you're basically always, in practice, integrating downhill in free energy. You're not waiting in the reactant basin for some lucky trajectory that takes you up to the transition state. You're starting up at the transition state and always integrating down towards the reactant. So that's a tremendous savings. You cut out all of the waiting time in the basins. Okay, coming back to what Benoit said, then you'll remember that the rate is basically the flux into the product basin, which we're going to pick out with this indicator HB, for trajectories starting in the reactant basin, which we're going to pick out with this indicator HA, divided by the concentration basically in the reactant well. And what you can do is rewrite this as basically an integral over these path probabilities. And so what it actually means in principle is that you could get the rate from asking what is the work that I have to do on these trajectories, on these paths, to constrain their endpoints to the product basin, given that I started them in the reactant basin. So I could imagine, although this isn't actually how you do it in practice, I could imagine just launching a whole bunch of trajectories from the reactant basin and asking how much do I have to do to kind of squeeze those trajectories down onto ending in the product basin. How much work did I have to do to kind of pull them over the barrier and get them to end in the product basin? That turns out to be kind of a tedious thing to do. And so what people actually do in practice, if they want to use these kind of path sampling methods for getting rates, is they actually break the problem up into a slightly different kind of umbrella sampling than the one that Benoit talked about, which is, say here's my reactant A, and here's my product basin B. What they'll do is they'll divide up the space between A and B with interfaces that don't cross. And then they'll ask, what's the probability that I got from this interface, say lambda 0, to this interface, lambda 1, so on and so forth. So it's almost the same kind of thinking as we employed for the path probability, except now it's in interfaces instead of in microscopic states. And then what you can do is basically get the rate from a product of path probabilities. And this is even more efficient than the whole path sampling, because now I have very little kind of decay, in essence, going from this interface to this interface. Not as many trajectories are going to fall back and lose. I can amplify the ones that got to the next interface. Okay, the next slide, it's got a whole bunch of references. They're basically for you to have in your file when you go home, okay? So people have followed these interface methods a lot over the last decade or so and done a lot of advances that now make these really actually, I think, close to kind of as good as you can get, okay? All right, so I'm basically going to turn it over to you now, but in essence what we're going to do now is say, well, if you were to do the path sampling procedure that I described for you, which you can, like I showed you, you can do it for a good-sized system, that DNA repair protein, it probably had about 40,000 atoms with the solvent and that kind of stuff. So, you know, it's not a small system. But you're running trajectories that are real dynamic trajectories. So they contain a ton of information in them, basically. But if you think back to what Benoit told you at the start, to actually get a rate out, you don't need quite that much information, or even to get some mechanistic insight. You might want basically the free energy, minimum free energy path, some recrossing probabilities, those kind of things. And so what Benoit's going to talk to you about is how much you actually get, essentially, probably not formally, the minimum free energy path using a method that's better suited for really big systems, where you just want to kind of get rid of some of that extra detail that's contained when you have like whole trajectories. So that's the string method, which Benoit can tell you about. I didn't press anything.
Right. So we've seen that if a system is just a simple, projected onto one simple one-dimensional or parameter, you may think you see a barrier like that, and then intuitively you'd like to proceed to describe that system. But from the transition path sampling, you can see that in fact reactive trajectories are complex, and they exist in the real molecular system as objects that are in the super high dimensional system. So any projection is always dangerous. For example, a double whale potential like that, when you look at it along one order parameter, may actually be two whales in the two-dimensional order parameter, and in fact, crossing here will certainly incorporate dynamics along the Z2 coordinate as much as the Z1 coordinate. And you can imagine that if you want to describe a process in more and more high-dimensional space, you get these potential of being forced in super high dimension at some point. What is the reason for this? In fact, Aaron did not mention it, but when you do these interfaces, even in TPS, when you do these interfaces, this lambda that he showed a bit before, and you want to follow trajectory, the lambda is a kind of order parameter. Now, when you do TPS, you don't necessarily assume that the dynamics is sort of harnessed by the lambda. You just use the lambda as a computational device to monitor. But if you pick the wrong lambda, or lambda that is useless, the TPS will struggle even more. And so, even in the context of TPS, it is very important to be able to pick order parameters that are as telling as possible, as probing of the reaction. And so, there are methodology that will try to not map the entire free energy surface. Imagine if you can do umbrella sampling probably in 4 or 5 dimensions for some systems, but beyond this is essentially not feasible. I mean, the size of the computation becomes so horrendously big, it makes no sense. So it certainly makes no sense to try to map out the entire function, but there are a complete set of methods that do not aim to compute the full surface, just aim at finding a pathway in that space that would go from one basin A to a basin B according to some minimum free energy or more likely pathway, more probable pathway. And so this is again a bunch of references, and those are within the context of a string method, so-called. Sometimes people call that also nudge elastic band, which is not exactly the same thing, but it's a similar method, and so or it has some similarity. And essentially it boils down to this. It's like, imagine you have 2 wells. You want to describe the pathway. In a computer, everything is discretized, so of course your pathway will be discretized too. So you're going to describe the pathway as a chain of configuration of the system that's able to take you from one basin to the other. And the best pathway, for example, in this case, it goes through this saddle point here, so definitely a straight line would be awful, because it would go through a wall of energy. So this is very, very unlikely, but this pathway is more likely because it goes through the saddle point. Now, how do you define that pathway in a super high dimensional space? Well, one way to define it is to say, at every point along the pathway, if I could hold the system there and let it go freely, I would like that system to actually flow down along the line. So this is a kind of self-consistent definition. Say if I have the pathway and I can have a system anywhere along the pathway and I let it free, it should flow along the pathway because that's the pathway of maximum probability. So if I could be here and I flow like that, in a sense of a Brownian dynamics, what I would have is the drift of the system would be the force times the diffusion tensor. And so the curve here is such that d times f, the component perpendicular to that is 0. So that means that essentially this is parallel, this is the tangent to the path. And so you can see now we don't really need the entire free energy surface anymore, but we will need to know this quantity at different places along a line. Now, in the variant that we have used, which is called the string method with swarm of trajectories, we don't actually compute the mean force or the diffusion tensor. What we do is we sit, let's say this is a trial pathway that is not so great, and then you go sit at the copy of the system, for example this one, and you release it. But you release many of them. And so many of you release a swarm of trajectories. These are all copies of the system. They're all going to drift. You can see here it's drifting a little bit more on the left side. So this is a clear sign that actually the pathway is not the optimal pathway yet. And so if I do the average, the mean drift, you'll see that the mean drift is off the black line. So that means I have to update the black line to get a better pathway. And so when you actually repeat that process, little by little, you're going to improve the path. One thing that happens though is that as you let go the systems, they will drift downhill and they will tend to underpopulate the top of the barrier. So there's a procedure, because what you're interested in is this line, it's a curve, and parametrically you want to really sample that curve very well. So there's a procedure called reparametrization in which you readjust the distance between the black balls so that they will all populate equally well at the top of the barrier. And so that gives this. I believe this is a movie that should work. Yes, and so this is, you can see here that the pathway will end up in this well and this well. I think if I play it again, it goes very fast because it's too easy. So it starts actually with an awful guess. Look at it, and boom, it drifts right away into the wells. And so this is the result of iteration of the string method with swarm of trajectories. And so essentially, it's able to optimize a pathway like that. It's been tested on multi-dimensional systems. For example, this is a protein involved in cellular signaling called NTRC, and it undergoes some sort of conformational change. So what we did, this was work that Albert Pun did in the lab some years ago. We made a model that was a simplified model. It's called a elastic network model, a two-state elastic network, and we find the pathway. So it's a very simplified model, but it's nonetheless a multi-dimensional model in which there are two stable states and a non-trivial saddle point. And so we found the pathway using the string method, and using the pathway at the top of the barrier, you can run trajectories, and then you find that actually most trajectories that are at the top are reactive, which is important because it means that you really have found a kinetic bottleneck there. If they were not really reactive, this is the distribution of the committer. If they're not really reactive, what you would get is a very flat distribution. So if you stand a little bit on the right, they are up. Actually, this would be on the left. They tend to go back to this well. If you stand on the right, they tend to go back to this well. And so it's really a kinetic bottleneck. And now Aaron will talk a bit more about additional application of the string method.
Yeah, that's just one slide to say that once you get these trajectories, oftentimes actually your work isn't done, which is you have now, in essence, a path in a very many-dimensional space. Usually what you'd like to do then is ultimately extract out some kind of story and potentially even experimentally probable insight. And so something that we really don't have time to talk about today, but again, we gave you just some references there, is how do you go from trajectories to identifying physically meaningful reaction coordinates that actually are predictive for these committers or probabilities that Benoit just showed you. In other words, how could I find a physical variable that'll tell me whether I am basically, I guess here, a reactant, a product, or a transition state where I've got a 50-50 chance of going towards the products or towards the reactants. And so something that we did some years ago was use machine learning methods to try and correlate those splitting probabilities with physical variables. Some other people like Cecilia Clementi at Rice have done some really nice work where they've used what are basically more sophisticated versions of principal component analysis to analyze the path. Okay, so this is just kind of a brief summary of, from a chronological perspective of what we told you already, which is that if you go way back to the early 90s, we didn't talk about it too much, there were some of the references. There are minimum energy path methods. Then we talked about how you can make real dynamic trajectories using the shooting method, transition path sampling. And then people realized that maybe you don't need all that information. And so to focus a lot on the string methods and the splitting methods for rate calculations. And then I just mentioned a little bit about interpretation. Okay, so part of the point of this workshop is to bring you all the way up to this moment in time. So I just want to give you a teeny little taste of some things that we've been working on to build on these methods in the center very recently. So even with all of these advances, where you have cut out the waiting time of sitting in, say, the reactant basin, and you're able to just focus on the trajectories that are taking you across the barrier, even with all of those advances, these calculations can still be pretty computationally expensive. And so what we wanted to do was to come up with a way where you could use a coarse-grained model to actually speed up the convergence of the string calculations that Benoit will work on. So to give you just a teeny little flavor for that, what I want to do is I want to write what you've already seen in a very compact way. So this Z here, that's the path in the collective variable space, okay, at some particular iteration of the optimization. So that might be that really bad guess that Benoit started off with, or a couple steps later. And then this S operator, that's going to be all of those string operations that he told you about. The launching the swarms, the reparameterization of the path to get even space images in the arc length, so forth. And all of those together are going to give me a new guess for the path, right? Okay, so once the path finally gets down to the minimum free energy path, then we should get out what we put back in. That means the simulation converged, right? Okay. So now what we're going to do is we're going to add to this some extra terms that are going to mix in the coarse-grained model, okay? All right. So imagine that I add to this two different coarse-grained terms. So these are just the same kind of string operations on now the coarse-grained model. I'm going to do one on the m+1 iteration and one on the m. So what does this mean? This means that if I manage to converge, then the path that I get out will be the same as the path that I got in, and these two terms, they'll be the same. So this whole square bracket will cancel out. And that means that my original string operation with the fine-grained, presumably more accurate model is still going to be stable. I get back what I started with. On the other hand, the only place over here on the right-hand side that I've got the next guess that I want to generate, this m+1, is over here in the coarse-grained model. So what that means is I can do one shot on the fine-grained string calculation, as well as one shot on the coarse-grained string calculation. then I can iterate a whole bunch of times with just the coarse-grained model in order to really explore, to take kind of a big step, if you will, in the collected variable space. So I can move the string along a lot faster, doing lots of calculations in my cheap coarse-grained model and relatively few calculations in my expensive fine-grained model. So that could, in principle, speed up these calculations quite a bit. So does it? This is active, looking at the flattening of the monomer. Here. But in essence, these two lobes kind of come together. You've probably seen it in some of the other talks since it's our workhorse molecule in the center. And here's comparing the regular string method with the multiscale method. And you're getting a speed up for, well, I should say this is the these elastic network models that Benoit mentioned, so it's a relatively simple problem. It's only the atoms that you see here. I don't have all the side chains and stuff. We're getting a speed up of about 4 to 5 fold. So that's something. Here's, I think, actually an even kind of cooler idea, and it leads to what Cheney is going to tell you about. Here's some calculations from Sayed Khaleh, who is a postdoc in this range. He's in the back there. You'll meet him, I think, this afternoon in the workshop. But instead of doing like a fine-grained and a coarse-grained model, what you could do is use a cheap quantum chemical method to speed up the reaction path calculation for an expensive quantum chemical method. So here, we're looking at cyclization of glucose. Our kind of good model, if you will, is DFT calculation with a VLib exchange correlation functional. And then we're using a really down and dirty semi-empirical method for the coarse-grained model. What you can see here is that, again, the relaxation of the pathway, you're getting about a kind of 10-fold speed up. So imagine that you could speed up your chemical reactivity, your quantum chemical calculations by a factor of 10, you'd be thrilled, right? So we think we have the potential to do that. Okay, so with that, I'm going to turn it over to Shane, who's going to tell you about how we're thinking about these kind of problems in a QMMO setting.
Okay, so I'm going to talk about some of the applications we've done for this string, and I think 2 applications. But before I want to do that, I want to kind of take a small step back and talk about QMMM methods. And I know a lot of you guys are probably very familiar with this, so it might be just a review, but I think it's kind of nice to get on the same page. So let me first take a giant step back, and let me just say that I like this plot a lot because it's just basically a hierarchy of methods, and it kind of shows that, you know, as we increase the accuracy of our methods, so this should be like an overclustered or a couple cluster down here on this side as well. As we increase this accuracy, we can only really apply them to rather small systems. So this is like a few atoms, and on the opposite side, if we have, you know, coarse-grained methods that we talked about here in the center, or even force fields, we can apply them to rather large systems. So the goal always is to essentially push this boundary, so this boundary of current methods, further up to the right. And so each of these methods has its own strong suit. So we have partial fog, we have some empirical methods that Professor Dinner talked about before. But so the motivation behind the QMMM approach is essentially that we have quantum mechanical methods are very good and they're very applicable to a wide range of very small systems. You can get molecular properties, you can get energy structures, you can even get reaction pathways pretty well. But again, and you don't need to determine, there's no parameterization needed to determine beforehand. And on the opposite side, we have MM methods, which are very quick and very fast, and they're very applicable to very large systems, but you have to go in beforehand and parameterize it as best you can. So the goal is then can we combine these two methods to take advantage of both of their strong suits as well as minimize the disadvantages. So that's where we have this QMM approach. It's very simple. We have a big region here. We have a small region, let's call it region A, where we are want to see some interesting chemistry. So, for instance, a reaction path or some specific proton transfer. And then we have region B here, where we don't really care too much about what's really going on. It does play a part in the overall reaction, but it's not so important. So this hybrid or multi-layered approach allows us to take advantage of both the MM and then the QM regions. So this QM region is this electronically important environment. So just to kind of formalize this, total energy, if you want to write it like that, the total energy is going to be the sum of this quantum mechanical energy, which is region A, this MM energy, which is region B, and then this interaction term, so the QMM part. So the quantum mechanical energy is rather straightforward, at least noted pretty simply. And we can do any kind of method we want. We can look at the functional theory, we can look at molecular orbital theory methods. We can also look at semi-empirical methods. And on the right side we have the MM energy, and we have this bonded interaction terms, non-bonded terms as well. But as this says here, the most important part, the most troubling part is the QMM interaction. And again, I'm not going to get too far into this because I know you guys are probably very familiar with it. So different ways in which we can take it into account this interaction. One is called this mechanical embedding. And essentially what you do here is simply place QM region inside the MM region and allow everything to interact in that way. And so when you do that, you really have two isolated regions. It's quick and it's easy, but again, you don't get any kind of interaction. So you're just missing a lot of the chemistry and kind. You can also look at this in electrostatic embedding. And in this case, you're actually taking into account the MM region into the QM region by some kind of electrostatic interaction. You can also do some van der Waals interactions as well. And then lastly, something a lot more difficult is this covalent embedding. This usually occurs when you have some sort of bond that crosses over between the QM and the MM regions. So having said all that, I want to go back now to the string method and why we're using it and what we're using it on. And so one thing that we've been discussing a lot, and so I think it's kind of nice that we're doing this stuff because in the tutorial session we're going to kind of go over this and hopefully we will be able to look at the reaction pathway for this ATP system. So one of the interesting systems is ATP hydrolysis, and we all know what it is. It's very important. It releases a lot of energy when this terminal phosphate group breaks off. But the reaction pathway isn't really known too well. So some suggest it's associative pathway, some suggest dissociative. And so in any associative mechanism, we see that this alytic water, so water over here will come in, associate with this gamma phosphate. And then after that, the phosphate breaks off and is removed from the system. The dissociative mechanism is kind of the opposite. The gamma phosphate breaks off first, and then we see the alytic water come in and attach to it that way. So one of the questions we want to address, and not only in this gas-phase system, but in the actual protein that we're going to look at further, is what is the actual mechanism by which this happens. So again here I've just said that these cleavage of this terminal phosphate to the binding water, oxygen, converts ATP to ADP and inorganic phosphate. I've shown here the system and I've shown all the collective variables we use. So we have here the distance between the beta phosphate and this oxygen, the distance between the beta and gamma phosphates. We've also looked at the distance between the gamma phosphate and this lytic water oxygen, and then this oxygen hydrogen bond distance. And so for this string, we just did like a very simple regular strain where we looked at the semi-empirical method, so really cheap quantum mechanical method. We did about 500 iterations, so it's relatively converged. Along the string we had 16 images, so in each one of these images we did just a 2 femtosecond free dynamics. So I've shown here kind of what the variables look like. So this is going to be the initial state, and then here's the final state plot. So before I show you what the actual path is going to look like, I'm just going to show you this plot. This kind of goes back to what Professor Roux was talking about when he says that we make an initial guess, which is directly between our initial state and our final state, and we draw the straight line between those. And then we can kind of discretize this up into however many images we want along the path. And then we can kind of see how the path progresses as we run the simulation. So this, on the right, we have essentially the same plot, but we plotted it with the energy, so you can kind of see where the barrier is in the middle here. So I'm going to try to play this movie. Hopefully it'll work. So it's hard to see, but if you can kind of look at so yes, this is again the phosphate here, and we're going to hopefully see this oxygen connect to this, associated with this phosphate, and we're going to see some proton shuttling as well. So each one of these frames in this video is going to be an image along the string, along the path. Okay, so it's kind of hard to see, but I'll try to talk my way through it. So first we see the breaking of the bond between the gamma phosphate and this oxygen here. Okay? And while that happens, we also see that the hydrogen is passed between to this neighboring oxygen, and this then causes another hydrogen to be passed to this oxygen as well. So and then we see lastly the association of this oxygen to the phosphate group. So this is kind of a different orientation. It's a slightly different path, so you can kind of see a different pathway. So again, we have the gamma phosphate shown here. It's going to get attacked at some point by this lytic water. We're going to see some proton shuttling as well. Again, we see first the gamma phosphate breaks off. We see the proton hops to the neighboring oxygen. We see the oxygen kind of hydrogen kind of rearranged. And then finally the association of the lytic water to the gamma phosphate. So this is all nice and that's kind of great, but this is only for the gas phase system. Right? So this is not realistic at all. So what we really want to look at is what does this look like in the protein and actin, as we talked about it a lot here. And so one of the main reasons why this is important in actin is because there's a direct relationship or assumed relationship between the conformation of the actin protein and also the rate of hydrolysis of the ATP. So for instance, in F-actin, so that's the actin in the filament, you see that there's a 70 times faster rate of hydrolysis of ATP than in the actin in solution. So what we try to do is run this same path, but for the entire system using a QMMM simulation. And we did this with the VFT method, and we only were able to do about 50 iterations. So the results aren't really converged too well, but again, there's 16 images along the path, and we use 2 femtoseconds of free dynamics. And in this case, the collective variables are a lot like the ones I showed in the original slide. So yeah, you can't really see this at all. I just wanted to show you that this is a protein here, obviously, around. And in the center here, we have the ATP. So I have another figure so you can see better. So again, we can kind of see phosphate breaking off and the lytic water attachment. So you can kind of tell that this geometry is rather unstable or unfavorable, and this oxygen here is actually not even attached to the phosphate group. So this one obviously needs some more iterations, but the idea is that we can now be able to determine the pathway in this giant system, where before we couldn't do that. And so, okay, so Professor Dinner mentioned before that not only can we do this for some regular string, so when we have QMMM, we want to use like the DFT method. We can also do it for a multiscale string. So when we have a fine grain method, we want to use a coarser method. So one of the ideas is to use this type of method with a semi-empirical fluent and an MM field. Or, for instance, we can just simply use a semi-empirical method and exclude completely the protein and get some kind of coarse depiction of this ATP hydrolysis. And so, lastly, I want to mention the fact that I know you guys spent a lot of time with Swift yesterday, and the way this code is worked, it uses Swift a lot, and this is actually the script that we use, the main script that we use to drive the Swift. And so you can see here kind of the app call that you guys dealing with yesterday, and then this part right here is really just the files that are transferred. And we have a for loop that loops over all the images. And so this is all done in parallel with the Swift logic. And so it's really, really simple. Obviously, there's a lot more stuff on the back end, but it's actually very simple. So with that, I just want to thank everyone. Are there any questions for me or for Mr. Dinner or Professor?
How dependent are the paths you guys in the state dependent on the collective variables that you guys?
Yeah, so I think they're very dependent on the collective variables as well, depending on how long you run the swarm trajectories. So if you allow them to kind of run for a longer amount of time, you can choose less trajectory collective variables and you can kind of sample a larger space. If you do really short trajectories, you really need to kind of pick exactly the pathway you want to see it happen. If you don't, you're not really going to see something reasonable. So a lot of it has to do with kind of figuring out how long the trajectory should be. How long, 2 femtoseconds might be too short, maybe 40 femtoseconds is too long. So you have to kind of play around with that.
Yeah, I mean, maybe what I could say to kind of amplify that is, in like the shooting methods where you're really just running molecular dynamics and then checking in the basins, there you're going to be less sensitive to the variables that you use to define your basins because you're not actually using those variables for parameterization of the actual path. You're just using them at the end as a check. For the string method, the images, they're actually in the collective variable space. So, although I wouldn't say that, although I think, it is a very powerful method and you have a certain amount of freedom in what are the variables that you choose, obviously the path, you can't go out of that space, and so it's going to be limited if you choose very bad ones.
You have in the multi-scale course grading, but also a sensitive one, the one that when you switch between, let's say, from semi-empirical to DFT, something like that, that you're changing the entire energy landscape, and so your swarm workers are pushing you in one direction, and then when you switch back,
Yeah, so that's actually that's an excellent question, Glenn. So what you just described, which is that you would do some coarse grained, then some fine grained, then some coarse grained, is what you might call kind of the naive combination of coarse-grained and fine-grained strings, right? But in fact, actually, the whole point of the math that I didn't really justify in some sense, I just kind of quoted at the end, is that you're actually using, you're not actually going between the two. You're always using the fine-grained information and mixing it in with the coarse-grained. And so you're never getting that kind of sudden change where you're flip-flopping back and forth between them. And you're guaranteed actually convergence to a stable fine-grained string. So in fact, by doing it right, we think you avoid that problem, basically.
Well, the convergence criteria makes sense to me, but in terms of you're still doing some sort of dynamics in the coarse-grained.
But even as we're iterating with the coarse-grained one, we're still using the fine-grained information. What you have to tune is how much iteration do you want to do in the coarse-grained one before you redo a fine-grained calculation. And so that would be a way of tuning, in essence, how much fine-grained information you've got in it. So indeed, you might find that, well, you actually have to do the fine-grained one fairly frequently or kind of tone down the coarse-grained one. So like sometimes we have like a tuning parameter in there. But you can't, in principle, do any worse than the fine-grained one.
You never do the coarse-grained string
by itself.
Iteration.
Right.
That never happens.
You're saying you never do just a straight-on coarse-grained string operation.
There's another question.
Go ahead.
Somebody here. Go ahead. Yeah.
So how dependent is the final string, the initial pathway you started? I mean, I saw that the example that you showed was like you started with a completely linear interpolation product, equal reaction product. Now let's say there are like two competitive pathways, and so you start from a completely like a linear, like average pathway.
Yeah.
You find one, then how would you search for the other one?
Yeah, so you're not going to jump a barrier in the orthogonal variables. So if you start off with a guess that's close to one of those pathways, exactly like you said, you're going to relax down into that pathway. And so the only way I would say right now that you're really going to find that other pathway would be to generate other guesses and get lucky, essentially.
Or you would think it's like what they call the finite temperature string sometimes, or is that you sort of kick back your solution to, you perturb it and then relax it back. It's a kind of a temperature.
Yeah, you're still not going to jump a big barrier. There is a version of one of these splitting methods where somebody has been, Peter Bolhaus, has been pushing himself out of basins, pushing the particles out of basins. So there, instead of having interfaces between two states, you say, well, I have many states and I just want to push myself out of the state that I'm in. And then in principle you could fall into another pathway perhaps more easily. But I would say overall the multi-pathway problem is sort of one of the outstanding challenges with these kind of sampling methods. I think we have very good tools now for basically a single pathway refining a gas that could be extremely bad and getting something very good. But yeah, if I have like 2 or 3 competing pathways, or even worse, like 10, then I think there really are not very good methods for systematically exploring them.
It's the same as energy minimization of a large structure. You can find one minimum. That doesn't mean enumerating all the minima is much more difficult.
Right.
It's similar.
Is there another question over there?
So I think this is actually kind of similar to that, because I was a little bit interested in multi-pathways. What about a multi-step pathway? Like, I wasn't really sure if what you're doing would easily transfer.
So you mean like an on-pathway intermediate, for example?
Yeah, so, maybe A goes to B, B goes to C, C goes to D. Can you get your string to hit each of those points?
Yes, you could do that. And moreover, you could, if you knew that those points existed, you could break it up. So yeah, in fact, the DNA repair system that I showed you, there we actually had one really deep intermediate where the nucleotide is kind of out of the protein, but not yet back in the DNA. I don't know if you've had other examples there, but I mean, basically, as long as it's along the way.
You can illustrate that. If you optimize the string on a two-dimensional surface, which has like many saddle points and many stable wells, you will find them.
Yeah, as long as you know, as long as your endpoints are in your real final endpoints, then these methods are really good about bringing you down to whatever the sort of saddle point path on the free energy surface.
Perhaps one thing is worth mentioning also is that conceptually, both TPS and the string method starts a little bit from the premise that you want to go from A to B, but in fact many systems have many stable states, and you can go from A to B to C, you could go from and D, and maybe D can go to A and B as well, so you have a network of rates. And so then you would want to break it down probably in all the elementary steps. It's not, you're not necessarily just looking for one pathway perhaps at the end, but you're looking for a network of pathways that link all the states. So that's something to keep in mind.